Hello everyone, very good evening to one and all. Yeah, good evening Akshay Kumar. Good evening Steel Lata. Good evening Anthony Rebis. So good evening to all. So good evening to one and all. Thank you for joining fourth day of our master class. So let's wait for few minutes. Wait for remaining people. They are also join. Hi sir. Hi Manjustri Gowda. Good evening. Good evening to all. Welcome back. So today is day 4. Let's wait for few minutes. Yeah, today we are gonna see digital electronics. This very basic knowledge you must have if you want to become a hardware engineer, or if you want to enter into VLSI semiconductor field. You must know all basic things like a digital electronics, like a number system, Boolean algebra, logic gates, K-map, so sequential and combinational circuits, uh, and then latches, flip-flops, demux, encoder, decoder, counter, registers, and so on. So we must to learn all these things. Then only you will become a hardware engineer. In top company like Intel, Qualcomm, any AMD, MediaTek. There is a lot of companies. So good evening to all. Welcome back to all. So let's wait for few minutes. Then we'll start. So let's wait for few minutes only. So good evening Pavitra. Good evening Sri Harsha Tamastri. So very good evening to all. Good evening Joshua Jesus. So good evening Anjali Devi. Good evening. So good evening Lakshmi. Welcome back to master class day 4. So yeah, we can start our session. So welcome back to all. So we'll start our session. So before going into digital electronics, so I just want to ask some interview, like a tricky question in digital electronics. So if you I hope you guys are know 2x1 mux. So this is multiplexer. So input of 2x1 mux is a input 1, input 2, and then selection. These are the inputs of 2x1 mux, and outputs are out. So there is a 2 inputs, 1 output, 1 selection line. So this is the information about 2x1 mux. So and then the question is, you can build the any logical gates by using the 2x1 mux. So this is the one interview questions. So I just sharing to you. So this is the answer for that. So by using the 2x1 mux, you can create any logical gate operation. So this is example for that. So welcome back all. So thank you for joining. So thank you. So yeah, so this is the, you can see this is a truth table for AND gate. So you can see here both inputs are 1, so we get 1. And then if you if any of inputs having 0 means you will get 0 as output. So this is a truth table for AND gate. So this is the 2x1 mux logic of AND gate. So this is the name is called realization of logic gate by using the 2x1 mux. So you can see here, basically firstly you have to analyze the truth table for AND gate. So we know that mux having the two inputs, three inputs, selection lines, one selection line, and then input 1, input 2. So if you selection line equal to 0 means, it will choose this line. If you selection line equal to 1 means, it will choose this line for the output. So let's analyze the truth table for AND gate. So if I take selection line as A, means if A equal to 0, means check our output, it's 0 only. So if there is a two conditions, if you take A equals 0, so my outputs are 0 0, and then B having the 1 and 0. So there is no same thing or alternative thing of B and out. You just have to compare these things like a B and out. So I'm having the if my selection line, if I'm taking A as a selection line, if A equals 0 means I will get the output as 0. So I just given for, if A equals 0 means it will choose this line, so I'm giving 0 for the input 1. So if I change my selection like A equal to 1, so A equal to 1, there is a two conditions like a 0 0 1 1. So you can notice here output will get the same value of B, whatever it having the B value. So 0 1 it having, so it will give same thing as output. So we can say we can pass the B value, whatever it having the B value, for the second output, so second input. So I'm assigning B as the output for output of mux. So if I choose A equal to 0 means it will choose here, you will get the output of 0. Yeah, good evening to all. So and then if I give the A equal to 1, it means it will choose this line, you will get the output of B. So if whatever it having the B values, it will give same output here. So for verification, you just take any of this combination of inputs. So I'm taking this, so A equal to 1, B equal to 0. So I am passing the values A equal to 1. If A equal to 1 means it will choose this line, you will get the output of 0. So you can see, if A equal to 1, B equal to 0, output is 0. So you will get the same thing. So if you take A equal to 1, B equal to 1, so if I give A equal to 1 here, so it will choose this line, and also B, I am assigning B equal to 1. So you will get the same, you will get the 1 as output. So this is the realization of a logic gate using 2x1 mux. So we can do any all logic gates. So for that, I'm just, for your clarification, I'm just writing for the XOR gate. So you can see here XOR gate is a truth table for XOR gate. If both inputs are true means, like if I'm taking A as a selection line, if I'm taking A equals 0 means I will get the same thing of B value. So you can see B 0, output also 0, B 1, output also 1. So and then if I take selection line A equal to 1, so I will get output as B bar. Why means here B equals 0 and my output is 1, so it is a complement of the B. And then here you can also see B equal to 1, output is a 0, so complement of B. So I can say, if I choose A equal, if I select A equals 0 means I will get the B. If I select first like A equal to 1, I will get the B bar. So just write the 2x1 mux logic here. So first I am taking A equals 0 for the XOR gate. So XOR gate means it will choose this line. So I want to write the A equals 0 means I am getting the same B value. So just pass the B value here. So I am getting the whatever it have. If I choose A equals 0, it will select this line. It will give the same, whatever it having the B value, it will give us the output. So and then if I choose A equal to 1, so you can see the complement of B is the output. So I just write B bar here. So this is the y is the output. So this is if you the a is a equal to 1. Yeah, a equal to 1 means it will choose this line. This line it having the b bar complement. So for verification purpose, if I take this inputs like a equal to 1, b equal to 0. So a equal to 1 means it will automatically choose this line. So by my input signal of b is 0, so initially it having 0, but complement of b is 1, so I will get the output as 1. So you can notice here my output is 1. From this circuit also we are getting same output 1. So this is the logic. Using the 2x1 mux, you can write logic for all logical gates operations. you may expect this interview questions while you are attending your interview. So just try remaining logic gates using 2x1 mux. So this is the thing I want to share to you. So I just move to our digital electronics. So today we are gonna see number system, Boolean algebra, logic gates, K maps. So firstly we are gonna see a overview of digital electronics. So digital electronics involves circuits that operate using the digital signals. We know that digital signals is digital signals like zeros and ones. These are the digital signals we having. So and then fundamental concepts include number system, Boolean algebra, logic gates, K maps. These are the digital electronics basics. So basically digital means a combination of zeros and ones only. So and then let's move to what is number system. So number system is a way of represent the number using the consistent set of symbols. So this is a number system. It having a lot of, we know that we having a lot of number system like decimal, binary, hexadecimal, and octal number system. So we'll see one by one. So if you having the base 10 number system, we can say that is a decimal. So you can see the decimal means it having the 0 to 1 values like a 0, 1, 2, 3, 4, 5, 6, 9. And then base 2 means it is representing the binaries, so zeros and ones. So and then octal means we have the base 8, it has 0 to 7. Hexadecimal means base 16, it has 0 to f. So f means if you 0 to 9, we know that decimal. After 10, 11, 12, 13, 14, 15, we can say that a, b, c, d up to f. So if you write in hexadecimal, you have to follow this condition or rule 0 to f. So thank you guys, thank you, good evening to all, welcome. So and then let's see the decimal number base 10. So here you can see, if you take this number as in example, this part is called as integer part, this is called fraction part, we know that. So this is the way of calculating the integer part of the whole base 10. So by multiplying the x power 10, 10 power 0, 10 power 1, 10 power 2, 10 power 3 for each and every integer, you will get the 3536. Same thing you have to follow for fraction also. So this is a basic thing. And let's see the binary to decimal conversion, decimal to binary conversion. So decimal to binary conversion means the decimal means it having the base 10, so it having the decimal values like a 0 to 9, and then we have to convert into binary, so in the form of the zeros and ones. So for that we can use this method. So you guys are know about like 8421 conversion, like if you want to convert to decimal to binary means using 8421, so 1001, we can say that is a binary form of the 9. Same thing you have to here using 1001. By multiplying of s 2 power 0, 2 power 1, 2 power 2, 2 power 3, you can get the decimal form of the we will get the decimal form. So this is also basic thing. I hope you already know about that. So this is a table for a binary, octal, hexadecimal. So decimal means we know that 0 1 2 3 4 is a decimal values. Binary means it will consist of zeros and ones only. Octal means 0 to 7 only. So and you can notice here, so 10, so after up to 7 it having the correct value like a 0 to 7. After the in the point of 8 it having the 1 0 in octal. Why? Because of by converting this, so 8 we can 8 is a decimal, we can represent in binary means 1 0 0 0. This is a representation of the 8 in binary. Just group this first 3 LSB bits. So if we group means we having one value like a 0, so that 0, that is a this 0. So and then 1, I just write that 1. So this is the way of converting the binary to octal. So by grouping the LSB 3 bits and then convert into single bit like a single octal bit like a 000 means 0. If you same thing, if you see in here like a 0 0 1 1, so 0 1 1 means you can see 0 1 1 means 3. So I just put 3 and then 1, so remaining 1 I just keep it here. So this is the conversion of binary to octal. So let's see one by one. And then we know that hexadecimal having the 0 to 9, so decimal values. After the 9 10 11 12 having alphabetic values like A to F. So A means 10, B means 11, C means 12, D means 13, E means 14, F means 15. And then this is the octal to binary conversion. So octal to binary conversion means we having the octal value. So this is my octal value 374. I have to convert into binary. For that you just need to convert the octal value into binary, and then you how means, so I'll just show you. So 4, we can write the 4 in binary means 1 0 0, so we can write like this type. 7 means 111, so 8, you guys may know about 8421, so it is used for binary decimal conversions, same like that only. So 7 means 111, this is called 7 in binary, this is called 3 in binary. So this is the binary conversion. After that we can neglect this 0, so neglect this 0, nothing will happen, but this is a rule. So we have to you have to neglect the unwanted 0 from the leftmost bit and rightmost bit, and then form some binary values. This is the binary value of 337. So this is the octal to binary conversion. So and then we'll move to binary to octal. Same thing we have to follow. We have the binary numbers, we have to group by 3. So you just keep into mind means if you converting binary to octal or octal to binary, group the binary values in by 3 bits. This is a shortcut method you have to take into mind. So and then just group it by 3 bits from the LSB side. For the integer part we have to go for left right to left like this direction. For in fraction part we have to go for left to right in this direction. So this is one rule. So and then I grouped it by 3 bits like 1 0 0 1 1 0 1 from this binary. So I just add the zeros to fulfill the 3 bit of octal value for completion. So I just add 3 bits, 2 zeros in the third group. So I just this is the binary form of this value, like so you can group by 3 means 1 0 0, we can say this 4, and then 1 1 0, we can say this 6. So remaining 1 is there, so just keep it here. So 1 6 4. Same like this here also 1 0 1 2 0 1 1 0 1 1 3 and then 1 4. So this is the kind of creating. So this one, so you can here we can remove the zeros, but if you in fraction part, if you having a last bit like a single bit for the last group, you just add to you just add to group, like add two zeros. So you can see here this, so this is 0 1 2 2 0 1 1 3 and then 1 0 0 4. So and then let's move to hexadecimal, hexa to a binary. Yeah, so hexa to binary means we can converting into hexa value into binary. This is my extra value. So f means we know that 15. So in the binary representation we can write this like way. So 1 1 1. So 2 means 0 1 1 2. So this is a conversion of the hexadecimal to binary. So and then we move to binary to hexadecimal. These are the basic easy basic things you must know. So it is also easy only. So by converting the binary to hexa, this is my binary value. So I'm converting into hexadecimal. For that I am grouping by 4 bits. So I'm just adding the additional 2 zeros for the last group. So and then converting the first group like 1 1 0 means like 1 1 0. It means 8 4 2 1 like 14. So 14 we can represent a 14 in hexadecimal means E. So we can see E. So and then 1 1 0 0. 1 1 0 0 means 8 plus 4 12. So C. So we can write this in hexadecimal form of C. And then 0 1 2 0 0 1 0. It we can write as 2 in hexadecimal form. So we can write as 2 CE. So this is the way of writing the conversion of the binary to hexadecimal. So and then let's move to the hexadecimal to octal. Same thing. We have the hexadecimal of 2f point C416. I'm just converting the hexadecimal to binary. F means 1 1 1 1. 2 means 0 1 0. So I'm grouping by 3. Why? Because of I'm doing the octal conversion. So I must have to, you should have to group by 3 bits. So I'm just grouping by 3 bits like a 1 1 and 1 0 1. So 1 1, so this like a 1 1 triple 1 we can write in decimal form of the 7. So octal form of 7. So 1 0 1 means 5. So I just write the 5. So yeah, you can write like this, like a 1 1 1 7 1 0 1 we can write as 5. So this is a way of writing the hexadecimal to octal. So and then octal to hexadecimal, same thing, like you have to group by 3 and then you have to group by 4 and then you have to convert the binary to decimal. You have to write for that like a 0 0 1 0 2 1 1 1. So like a 0 0 1 1 2 0 0 1 2 2. So 0 1 1 1 we can write a 6. So 7. So this is the way of writing octal to hexadecimal. So this is a basic thing you should try at yourself. So it is also important thing while attending interview. They will ask some conversion like a hexadecimal to binary to hexadecimal. If you add practice means you will easily answer that, and then if you not practice means it will take time to converting. So you just try these things at your home, like a binary to conversion, hexadecimal to binary. So and then let's move to the promotion of our internship. So this is your opportunity. You can convert this masterclass into 1 month internship internship on FPGA. So these are the benefits you will get from the internship, 1 month internship. Yeah, you will get the 30 days of recording session, all 30 days PPTs, exclusive project codes, VIP community group for your doubt clearing, and also for internship updates. And then you will get the IETE internship confirmation letter from IETE, and you will get the 90 days LMX course access. and then you will get the assignments and tasks from our side to build your knowledge, and then you will get the weekly live sessions, resume buildings, mock test, internship certificates, and also participate certificates. These all benefits will get at the discounted fee of just 999. So our regular fee is 3,999, but in this session period you will get at a discounted fee of just 999. By using this link also you will get you can register for internship, and also our organizer will post the link on your chat box, so just use that link for your registrations. So this offer will close at 16th March, so this is a limited time period offer. Yeah, you guys are interested, means I hope you guys are interested. So let's move to Boolean algebra. So Boolean algebra is the mathematical foundation of digital circuits. So Boolean algebra means, we know that logical gates having the AND, OR gate, NOT gate. So by these gates we can do some algebraic or mathematical operations. We can do arithmetic operations by using the logic gates. Let's see the one by one how to do. So firstly we need to see what is difference between the ordinary algebra and the Boolean algebra. So we know that ordinary algebra means it having the addition, multiplication, division, like that. Same thing we are also having here, like if you here, but here we are using the separate names, separate keywords like AND, OR, NOT, XOR, XNOR, and NAND, NOR. So we are having separate operations. So you can represent in here A and B, A or B, A not B, so A not B not. So these are the Boolean logic gates. So let's see the one by one the logic gates. So before going to that, you should know about the what is variables, what is literals, what is terms in the equation. So if you take this example, yeah, you can see here A bar plus A and B, so A and B. If you read the equation, like you just read like A bar or A and B. So this is a Boolean algebra, so you just follow that rule. So just it having the two variables, like A and B is a two variable, literals are three. So literals means literals means nothing but A bar is one literal, A is a one literal, B is a another literal. So there are three literals in this equation. And then terms, there are two terms, A bar is a one term, and then A and B is a one term. So here I am doing like a OR operation, addition operation. So it is separating the terms A bar and A and B. So this is the terms. So and then let's move to the law of Boolean algebras. There are three laws, like commutative law, associative law, distributive law. So I hope you are you also read in your school and colleges. So let's see one by one. So commutative law means, this is the commutative law of like a plus b equal to b plus a. So we can write this, so both are equal, means a plus b is equal to b plus a. So both are same like equal ones. So we can say this is called a commutative law. So same for addition and multiplication. So a and b equal to b and a. So we can also write as a and b equal to b and a. So this is the commutative law of addition and multiplication. So and then associative law. So associative law means a plus b plus c equal to, we can write a plus b plus c. So we can write this way, like this is the associative law telling, like we can write, if the each and every terms having same values like a plus b plus c, means we can write we can separate by the variables by bracket, like a plus b plus c. We can also do this, and same like a and of b and c, like a and b of c. So this is the associative law. So just know this. So and then distributive law. So distributive law means it will multiplying the inside the bracket like a and b plus b and c. So this is the distributive law. And then there is a one important things, this like a plus b of b and c equal, it's not equal to a plus b and a plus c. So this is I'm saying this is not equal to it is not way to write a correct equation. You just write like a and b plus a and c. So this is the correct way of writing the uh, distributive law. So you just follow this rule like if you having the a and of b plus c, you just you have to write like a and b plus a plus c. So this is a distributive law. So and then we move to the rules of Boolean algebras. So there are several rules. It is that these rules are helpful to simplify the Boolean algebra equations. So if you having the logical circuit, we can convert into equation. By simplifying the equation, you can use these rules like a Boolean algebra rules. What there means, like if you add the a plus 0, you will get a plus 1 a a into 0 a. If you multiply anything from anything with 0, you will get 0. So you will multiply anything into 1, you will get a is anything. So a plus a plus a bar 1. So this is main rule, take into your mind. So a plus a bar equal to 1, a into a into a bar is 0. So this is a difference between the addition and the multiplication. If you add the a plus a bar, you will get 1. A into a bar, you will get 0. And then and then a double bar, you will get the output as a. This is a rules. So a plus ab, we can write a plus a bar b, we can write a plus b. So a plus b of a plus c, you can write a plus bc. So this is the rules. So up to 1 to 9 rule, it is very simple, easy to understand. But you can't some people may don't know about this a plus b, how it comes a plus ab equal to a. So let's see how it comes. So rule 10. So we know that a plus ab equal to a. Let's see how. So we can take out the a from this equation. So both terms like both terms having the a, this is one term, this is another term. So both terms having a, so which I just take out the a commonly. So I'm just after that I'm having a of 1 plus b. So we know that 1 plus a plus 1 equal to 1. So same thing. So 1 plus b, so 1 plus b means we have to put 1. So 1 into a into 1 a. So a into 1 a. So this is the way of converting, simplifying the equation by using the algebra Boolean algebra rules. So and then we'll move to rule 11. So rule 11 is a plus a bar b equal to a plus b. Let's see how it comes. So if you taken this, so so I just follow this rule we know that a equal to a plus ab. Already we know that we can write a like this way, like a equal to a plus b. So and then I can write also a equal to, so a equal to a. So you can see in the seventh rule, a dot a into a. So same thing. So I just write this a as the a into a, and then I'm adding the external a into a bar. So it means 0. A into a bar, I already said no, a into a bar, it means 0. I just taking out of a plus a bar. So take this, this is one, imagine this is the one term and this is another term. So it both terms are having the a plus a bar. So here I am taking the a, here I am taking the a bar. So I'm just taking the a plus a bar outs, and then it having the a plus b. So this is the factoring, like taking out tricks. So we know that a plus a bar equal to 1, so just put here 1. So 1 into a plus b, it means a plus b only. So you can see here, this is the logical circuit diagram for this equation. I'm converting into this like a simple way. So this is the rule why we follow the Boolean algebra rule. This is the reason why we follow the rules. We can simplify our equations. We can reduce our logical gates in our circuit. So let's move to rule 12. So our rule 12 is a plus b and a plus c equal to a plus bc. Let's see how. So and then I'm just multiplying this term and this term by using the distributive law. B, so a into a plus a into c, so a into a plus ac, ba bc. So we know that a into a we can write as a, and then I am taking the a in out here from these two terms. So I have remaining like a into 1 plus c. So and then factorizing method I'm following that. I'm just after that we know that 1 plus c equal to 1, and then 1 into a. So 1 into a means what? So a into 1 I will write as 1, I will write as a. So just write a, and then here I'm taking the here I'm taking some. So I'm writing this like this way, like a of 1 plus b, and then bc, and then here it having 1 plus b means 1. So I'm just write a into 1 plus bc. So we can write finally like a into 1. So a into 1 means a. So we can write it like a plus bc. So this is a simplification, just following the Boolean algebra rules. So you just know about that. So this is the basic logic gates, and or not. So AND gate will do the multiplication operation, OR gate will do the addition operation, NOT gate will do the complement, like opposite of input. Like if you give input 0, will get as output as 1. So this is the functionalities. So this is the truth table for the basic logic gates. And so if both inputs are 1 means you will get a 1 as output, or else you will get the 0 as the output. So and then OR operation by addition. OR operation means by doing addition operation. So if both inputs are 0 means you will get 0, otherwise you will get 1. If neither our input is or 1 means you will get a 1 as output. So same in NOT gate. So these are the basic gates. I hope you already know that. So this is the some waveform diagram for the basic logic gates. Like these are my inputs, like xy is my input. So my input, firstly I am having the input like 0 0, x equals 0, y equals 0, and the time I am having the AND operation output is 0, OR operation also 0. Why? Because of both inputs are 0. So and then I am changing the inputs like a 1 and 0 for x and y. So I'm just like and if you can see here in the AND waveform I'm getting 0, but in OR waveform I'm getting 1. Why? Because of by doing the OR operation of 1 and 0, you will get the 1 output. 1 plus 0 equal to 1. 1 into 0 0. You know that this is the same thing we seen in the truth table. So and then we'll move to let's guess the output signals, output of this circuit. Like this is OR gate. So I'm just adding the NOT gate input for this input for the OR gate. So this is my first input, second input A and B. So I'm just by using the NOT gate I'm passing the A input to B, but it will complementing, so it will complement it will give complement of a whatever given, like if you given like a 0 means here you will get the 1, so 1 plus 0 you will get 1. So if you give 0 or 1 you will get the same or always one output. So if this is for circuit for, you will get the always 0 output. So in the interview some people may will ask you, write the draw a circuit for, you will get always 1, you must always get 0 1. So on that time you can try this, you must your answer will be that, so will be this. So this is circuit for, you will get always 1, this is circuit for, you will get always 0 as output. And then we'll move to NAND gate. So NAND gate is opposite of AND gate. So and then NOR gate is opposite of complement of the OR gate. So just this is a symbol for that. This is a symbol for the NAND gate. You just see the bubble in the output wire. So this is a symbol for the NAND gate. So this is a symbol for the NOR gate. So this is a complement of the OR gate, and this is a complement of the AND gate. So and then we'll move to the XOR gate. So XOR gate is a little bit different. Why? Because of then you can see truth table. If your inputs are same, like a 0 0 or 1 1, you will get the output as 0. So this is the condition. So if your inputs are different, like a 0 1 or 1 0, you will get a 1 as a output. So this is the multi-input XOR gate. So just follow this truth table. So and then here it's some information about XOR gate. So XOR gate is something referred to as anything but not at all. So not all. So XOR gate is enabled only when there are odd numbers of digital ones. So odd number means we know that 1 3 5 like that. So if you using multi-bit XOR, if you are having the inputs of odd numbers of inputs, then only it will enable. So therefore XOR gate can be viewed as a odd bit check circuit. So if you someone ask write draw a circuit of a odd bit check circuit, you must to try XOR gate. So this is XOR XNOR gate. It is the opposite of the XOR gate. So if both inputs are same means you will get a 1 as output, otherwise you will get the 0 as output. So these are the basic gates. So let's see the universal gates like a NAND and NOR. Why we call universal gates like a NAND and NOR means by using the NAND and NOR gates, you can build any logical circuits and any logical gates. So these are the examples circuits for the why we called NAND as universal gate. So by using the NAND gate, I can build a NOT gate, I can build AND gate, I can build OR gate operations. So this is the you can write also XOR and you can create a circuit for XOR and XNOR gate using the NAND gate. So and then these are the circuits you just try at your home. So and also NOR also is we are calling the NOR is also universal gate. Same thing like a NAND, we can also build any logical gates by using the NOR gate like this. So just try you just try these circuits at your homes, pass some stimulus like inputs a equals 0 b equal to 1, check you are getting a correct XOR output or XNOR output by using the NOR operation, NOR gate. So let's move to the K-map. So this is the, so we are using the Boolean rules for simplify the equation, and then also we can do simplification by using the K-map also. So K-map also means is a 2D grid like a table. By using that K-map table we can reduce our equation, we can simplify our equation. So let's see how. So the K-map will introduced in 1953. So K-map it reduced the need of extensive calculation by taking advantage of human patterns recognition capability, and the required Boolean results are transferred from the truth table onto the two-dimensional grid. So this is the main thing. So required Boolean results are transferred from truth table onto two-dimensional grid. Grid means 2D table like that. So we'll see how it works. So for creating the K-map, you just know about variables. So for creating the K-maps, so you have to follow rule like a 2 power n. So if you having the two variable, you have to write the two rows and two columns. If you write in the three variables, so means 2 power 3 8. So it having the 8 min terms. So let's see what is min terms. So it having the 2 rows 4 columns to make the 2D grid for 8 variables. So how means, so before that you must know about canonical forms of K-map. It having the sum of product of sum. So let's see what is that. Yeah, this is the two variable. If you having the A and B, if you want to make it K-map for two variable, you have to draw the grid like this, 2D grid. So this is that. So for 2 power n, so you having the two variables. So 2 power 2 means 4. So you having the 4, you must have the 4 min terms. So these are the min terms. Min terms is nothing but combination of the inputs, like a equals 0, b equals 0. We can write the min terms m1 like a bar, b bar, a bar, b, a, b bar, a, b. So these are the min terms. So in the K-map, you just write the min terms like a 0th min term, first min term, second min term, third min term. So this is the creating the two variable, like a two variable K-map. So and then this is the creating of the three variable K-map. So 2 power 3 means 8. So totally 8 min terms you have if you using the three variable in your equation. So these are that like min terms, like if you inputs are 0 0 0, you can write a bar, b bar, c bar. So you just refer this table. So if you are writing the min terms, means you just follow some rules of K-map, like if first you have to write min terms here, and then 0 min term, first min term, and then you will move to this cell like a second min term, third min term, fourth min term, fifth min term, and then we will move to here 6th min term, 7th min term. So this is that. You must know about three variable K-map, so that so we can convert this masterclass into internship for your better knowledge. If you want to increase your knowledge in VLSI or FPGA, you can use this internship program. So internship on FPGA. So you will get the benefits of all the details recording session, all the details presentation, exclusive project codes, VAP community group, IETE certification, and also you will get the access of 90 days LMS course access. And you will get the assignment and tasks, and you will get the weekly live session, resume building, mock test, internship certificate, and also you will get the participation certificate. These three benefits, all these benefits you will get at a discounted fee of just 999. So our regular fee is 3,999. So you will get at a discounted fee of just 999. So you can use this link, and also you can use the chat box link to register yourself for the internship. So this is a limited time period offer. This offer will close at 16th March. So let's see quickly the K-map. So this is the equation. We have a bar b bar cd plus a bar b cd plus a b cd plus a b bar cd plus a b c bar d bar. So this is a big equation we have. So we have to simplify this equation by using the K-map. let's see how. So so let's take the first term, a bar b bar cd. So a bar b bar, where you can, so before going to that you must know how to write the k-map table. So 0 1 3 2, so you have to follow this rule. 0 0 means 0, 0 1 means 1, 1 1 2 3. Here also you can see 0 0 0 1 1 1 1 0. So we are regularly following like a 0 0 0 1 1 0 1 1. But if you are doing k mapping, so just follow these rules: 0 0 0 1 1 1 1 0. Same like for cd also. This is the input for a and b. This is the inputs for c and d. So if you take first term a bar b bar cd, so we can write a bar b bar means this, we can take this row a bar b bar. 0 means a, like a, we can write as a bar. So a bar b bar, I take this row and then I check for cd. So cd means here, just I write one here and then a bar b. So I take this row and then I just find for cd. So I just put here 1 for this term and then a b c d. So a b c d, I just put 1 here and then a b bar here. I take this row and then I check for cd. Same like cd means it, I put here 1. So and then a b, so a b, I take this row and then c bar d. So c bar d means like a c bar d. So I put 1 here and then a b c d bar. a b c d bar means here I am putting 1. So this so I just give 1 based on my equation on the k-map table, and then we have to group the ones in the k-map. So firstly we have to look for 8 group, and then 4 we can group like 8 bits, 4 bits, 2 bits, and then 1. So in here in this k-map we don't have 8 bit of grouping, so I just group like a 4 bit, like this is one group and then this is another group. So and then I'm writing the simplified equation. How means, just take this one group. Here we can see a b are same like a 1 and 1, so I just write a b. And also you have to note, you have to see here the values are changing like a 0 0 0 1 1 1 1 0. So we need to remove that. We don't need to write the cd part for this group, so just write a b. Same like that, if you take this group, here you can see a b inputs are changing, so I just write cd. So this is the grouping and writing the k-map equation. So I'm just simplified this equation by using k-map as ab plus cd. So and then let's see another one example. So this is, we having the all sides of, so all corners of k-map 1. So if you apply this equation in your k-map, you just have this like this only. So I just grouped here this 2 and then this 2 and then this 2 like this. If you see this, like if you see this, if you take this 2, so this 2 group, so this is one group, this is this is one group, this is one group. So I'm grouping by the 2 bits. We seen this is grouped by 4 bits, this is grouped by 2 bits. So this is one group, then this is one group. So if you see, if you take in b, like a b, here a is changing but b is same, so we write b bar for this group. and then if you look for this group, if you have to look for this like here like this. So C is same changing, so here it having the 0 0, here it having the 1 0. C is changing but D having the same value, so I can write the D bar. So by using the K-map I can simplify this equation B bar D bar just by using the K-map very easily. So the rules are just to group by 842 bits, group for per bits, and then check for the values changing or not, or if you have the same values. If you have the same value like a B, we can write B bar. In here we having the D as the same values, so we can write a D bar. So this is the how to write the K-map simplification. So and then let's see some other equation like this is our equation. A bar B bar C bar means here you having the A bar B bar and C bar D bar, so I just put here 1. So you have to do same thing for the every terms in the equation, and you will get the values of 1 1 1 1 1 1 here. So I just grouped by 8 bits. So here it having the 4 bit, here it having the 4 bits, so I've just grouped by 8 bits. So imagine it's like a paper, I'm just folding, so like this, like that, sorry, so like this I can group. So I'm having paper in this side, I'm having some 4-bit value, here having some 4-bit value. I'm just grouping, means I'm just folding the paper. So by doing this we can group the I can group the K-map. So after that I'm just referring these two rows. So you can see 0 0 0 1. So if I referring this 2 row means 0 1, there is a changing of A 0 to 1, so we need to neglect that. And but you can see B having the 0 also, here also B having 0, so we can write output as B bar. So if you simplify this equation, if you can simplify using K-map as B bar. So this is the thing of K-map. So it is very easy to understand. It's a very simple thing, and it is also basic thing also. You must know what is K-map, how it is work. So that's all for today. Tomorrow we'll go to see intro of Verilog and data types. So tomorrow we'll see some basic program of our Verilog, like a mux encoder, decoder, and like circuits like a counter, shift register. So we'll see tomorrow how to write a Verilog code for that, and what are the syntax, and then what are the data types of Verilog, and then what are the level of abstractions in Verilog. Like it having a lot of level of abstraction, like behavioral model Verilog, and then structural model Verilog. We can write this model, we can use this model to write a Verilog code, and then data flow modeling style. So it having a lot of style to write the Verilog code. So let's see in the tomorrow session. So this is for today. Then thank you for watching, thank you for listening. So we'll see tomorrow. So yeah, thank you guys, thank you for listening. Yeah, thank you. Can we design NOT gate using XOR gate? I think you can try, so you can try it yourself, you will get also. We can design a NOT gate using XOR gate also. So anyone know? So I think it is difficult to cover the all digital electronic part in one session. So that's why I'm going fast. So if you take and came up, it will take up to half day to cover the all the SOF, POF, K-maps. So I'm just time for the time consideration, I'm going first. So thank you guys, thank you for listening. So we'll see tomorrow.